So we are just continuing with the same logic of testing hypothesis. Before we tested a hypothesis about a population's mean and population proportion, and continuing in that thread, we are now going to look at testing population variance. So for almost all the course, we are assuming that the population is normally distributed. And as you know, that if something is normally distributed, the only two things which you need to know about that distribution, anything else can be deduced from those two numbers, is one is mean and the other is the variance or the standard deviation of that normal distribution. So we have seen how to test, if you have a hypothesis, you have a belief that what is the mean of a certain population, how can you test that? Similarly, you can use the um similar ideas and similar techniques to test for the variance. That would be the second characteristic of a normal distribution. So how would you do that? Well, we have that we want to test population variance. Variance or standard deviation. It's one and the same thing. Variance is just the square of the standard deviation. So what we are talking about, we have certain null hypothesis about the variance. So for example, that is equal to certain number, or just as an example, let's say if less than a certain number, sigma naught. So when I make a square, that's just the name, that thing is called the variance. And you are testing it, if this is the case, you're testing it against that is more than this number. The variance is more than this number. How would you do it? Well, if you have this null and this alternate, that means you will be rejecting this null if the variance comes out to be. So first of all, you will be picking a sample and compute sample variance, because you are testing the variance of the population, so you are not assuming anything about, well, you are assuming a hypothesis, but you cannot use that to make any probabilistic predictions. So you pick a sample and compute sample variance, and from this try to conclude if H naught is valid or not. Let's see, what's the question? No, it's not hybrid, unfortunately. So try to conclude if H naught is valid or not. So what you know is that the sample variance, which we call S square, it has same mean. It lies somewhere around the true value sigma naught. Sigma naught is almost same. Is, or I should say, is distributed around the population value, which is sigma naught square. Well, let's say sigma square. Whatever the population value is, it's distributed around that. And how is it distributed? It's not normally distributed. Distributed according to chi-square distribution. And what's the exact relation? The chi-square distribution is related to this random variable. This is a random variable according to this. This is a random, so this is also random. And there's some scaling and some squaring involved, but they are related. So if you know one, you can conclude about the other. And this fact is very important, that we know that the expectation value of the sample variance is equal to the population variance. So that means if sigma naught were really the population variance, if H naught, if sigma naught were the population variance, sigma naught square, population variance, you would not expect a value of S square which is very far away from sigma naught square in the sample, right? Because this chi-square variable is not symmetric, but the mean is around somewhere around sigma naught square. So if you see a number very, very far away over here, very, very far away over here, then there's a very less likelihood that it came from a true population variance of sigma naught square. A number, probability of getting a number here or here is very small. So you can devise tests based on these probabilities. So you say that if the probability of this chi-square variable being greater than a certain, let me write it over here, draw it again. Here is kind of chi-square distribution. There is some critical value. Probability of your chi-square variable. So you construct the chi-square according to this formula by choosing a sample and computing its sample variance. If this chi-square variable which you have computed, this has this number coming up greater than this critical value, has a probability alpha. That's how I have defined it. This is the value of chi nu alpha over here. On the x-axis, I have chi nu values. So there's a critical value chi nu alpha. So that chi nu square being more than that, I'll sometimes miss the squares, they are always there, it's just a part of notation. Chi nu square being more than that has a probability alpha. That's how you are defining this critical value. So obviously now you can define kind of a test that if I have my hypothesis that sigma square population mean is less than particular value of sigma naught square, then the alternate is sigma square is more than this value. So I will reject it if I see a very large number, a very large S square. How large? Which lands me somewhere here. So reject with a significance alpha if this chi you have computed, which is this number, is greater than this critical value. Because a number, a chi-square, which you have computed, landing over here at this, in this region, has a very little probability. So you set that limit by choosing an alpha. So alpha would be typically, again, 0.05 or 0.01, whatever you choose, that's the significance level. And landing beyond that region has a small probability. And if that happens, then you reject your hypothesis that the population variance is less than this number, with the significance which is determined by how little probability there was to land in there. So in this case, I have essentially written it out, but let me write it more clearly. So if your H naught is sigma square is equal to sigma naught square, or H naught is sigma square is less than sigma naught square. And in both cases, if you take the alternate, that sigma square is greater than sigma naught square, a certain hypothesized value, then you will reject reject H naught if this thing square is greater than this critical value. Now you can have other kind of hypothesis that sigma is equal to sigma naught square, or H naught is greater than sigma naught square, and alternate is that the variance is less than this value. So now you are looking for a critical value here. Some kind of a beta. So that if you get a very small chi-square landing in this region, then it will have a small probability to occur. And if that happens, then you reject. So what would this number be? Well, if I start from here, that I had defined this, and remember, chi-square distribution is not symmetric. So I cannot just do the minus the previous number and take it to be on the left hand tail. This is going to be a different number. So if I had this chi nu alpha square, this I had defined it like that. Like that. And this area is alpha. Now I want to put this area to be alpha. Then this chi naught beta, which I'm calling P of chi naught square being less than chi naught beta square is alpha. But this same thing I can also write as P chi naught square being greater than this value beta is 1 minus alpha, right? Because this probability that chi naught being greater than this is 1 minus alpha. But this thing, I had called it from here that whatever probability is over here, put it here. So you can write it like this. And this same number can be found by this. This is the form we need. But what should be clear to you is the logic. There's this critical value so that chi square being less than this must have a probability alpha. So this thing, I'm going to denote it as 1 minus alpha. So this you reject if n minus 1 s square over sigma naught square is less than this critical value. That becomes your test on the lower end. Probably let's write it more clearly. If your hypothesis is sigma square is equal to a specified value and the alternate is that sigma square is less than this value, or even if this is equal or greater and the alternate, in that case you have only one alternate possibility. If this is so, then you can reject H naught if n minus 1 s square is less than 1 minus alpha. Similarly, you can do the two-sided. In that case, sigma naught square is exactly equal to sigma, a specified value, and the alternate is that sigma square is not equal to sigma naught square. So if it lands here, or if it lands here, you reject. So you can reject. First of all, you have to divide the significance half on the upper tail and half on the lower tail. So you can reject H naught if, using the above formulas, is less than chi square n minus 1 1 minus alpha by 2, or if this is greater than alpha by 2. Any of those conditions is met, you can reject it. So we can do an example. So suppose you have certain boxes which are filled and there's some impurity. There's box weight of chemical packages is 100 kg, and the impurity has a variance of sigma square is equal to 4 kg. This is the claim. Or let's say it's desired that variance of impurities is within 4 kg. So the impurities are randomly normally distributed. Some bags have more, some bags have less, but you don't want them to be have a very broad distribution. You don't want a lot of impurities to be there. And that could still be true even if the mean of the impurities is kept small. So you don't want each packet to have a high probability of having impurity. So that would be true if the variance is small. So this is desired and you want to test. So you make your hypothesis that the population variance is less than this value 4. Then your alternate would obviously be that it is more than 4. So a sample of 20 bags was chosen. And Measuring the impurities, it was found that the variance, because each bag had a different impurity level, and the variance turned out to be of impurities in this sample turned out to be 6.62. So that's the square of the standard deviation. Now we want to test H naught at alpha is equal to 0.05 significance. So what you have got here in the sample, you got a number larger than the variance of the population which you are expecting. So you want to test if my belief or if what I hope for the variance of the population, that it is kept within the value of 4, is that true or not? So that's the main thing which is being asked over here. So to test it, you have to first find out this critical value, chi 19.05, and since you are testing for, your alternate is that the variance is larger than the specified value. So you are looking for this critical value, which is on this end. So that means this you have to find by doing this. Or the same thing you can do by .95, because the same number, when you compute the area behind it, if this is 0.05, this is going to be 0.95. So to do that, you can go to SPSS, or let's go to StatTrack, because I don't know if many people have downloaded SPSS, but you really should. So let me change the screen. So degrees of freedom, we have 19. Why we have 19? Because we chose 20 bags. And the critical value we are after. So I'm going to leave this field like that. And since it computes the cumulative probability, so it keeps the chi-square less than this critical value. So I should put in 0.95. So it gives me a value of 30.1. That means when I do the test, I have to check this number, which is 20 minus 1. And here I put in my sample value, which was 6.62 over 4. So this gives me 31.445. And since it is greater than the critical value, which I just computed to be 30.1, so that means H naught is rejected. Now I can compute the p-value of this. Whenever you reject your null hypothesis, then at the same time you can compute the p-value too. So let us compute the p-value. So what would be the p-value? P-value is that you assume that I'm going to take that chi-square. So you landed here for chi-square. This was from your sample. How do you compute it? This number, which you just did. Sigma naught square. And this was 31.445. So as always, you take this value to be your critical value, and then you compute all this probability. So make this the critical value. And then you compute all this probability for which is the probability that you can reject the hypothesis given that you saw this value in the sample. So this probability is the p-value. The probability that this chi-square 19, this value, that your chi-square 19 is greater than this value. So you can go and compute it. Again, if I go to stat track, this time degrees of freedom still remain 19. This time you know what the critical value is, and you are computing the probability above it. So it's 0.004. So the p-value is 0.04. We can do a few more examples. So this is problem 9.49 from book. And it says that plastic sheets produced by a machine, they are being monitored for possible fluctuations in their thickness. And they are trying to monitor that, and they are trying to make sure that the variance in thickness does not exceed 2.25, so that all these sheets have more or less same thickness. So, and there will be a cause of concern if the thickness exceeds this value. So that means they have to monitor and make sure that variance in thickness does not exceed this value, 2.25 millimeters square. Now they cannot waste their whole life trying to make sure that this remains below it. So they start with this null hypothesis. They have optimized their processes so that they believe that this is what's happening. So that's why this is their null hypothesis, that the variance is equal to 2.25. And if this is rejected with this alternate, that the variance becomes larger than this, then they're going to reject it. And they are doing it obviously by picking some samples. So in a sample of 10 randomly selected sheets, in a sample of 10 randomly selected sheets, they find these numbers. These thicknesses. So what are these? 226, 226, 232, 227. So each sheet has a different thickness, as one would expect. They just want to make sure that they're not very different from each other, and the variance does not exceed that value. And they're going to do it by picking this sample of 10 sheets. These are the numbers they got. And then they compute the sample variance. And after they have computed the sample variance, they're going to decide if the sample variance is way beyond this number, 2.25, then they're going to decide, did this happen by chance, or is there a cause of concern? So even if they reject, remember, even if they reject it because they see a very big number, even then there is a probability that the population variance is actually limited within this value. They're just doing a statistical analysis. So they test at alpha is equal to 0.05, the null hypothesis. So how will you do it? Well, you can go to SPSS and to do these computations, let me do the share. And let's put in this data, 226, 226, 232, 227, 225, 228, 225, 228, 229, and 230. This was our data. I can give it the name, thickness, and now you can just do the descriptive statistics to compute the sample variance. I don't need all these. Let's keep the mean there, it doesn't matter. I can directly compute the variance. So the variance is 5.156. So let's store it here. 156. Let's increase the decimals. And given this variance, now we have to test. So I compute the chi-square variable. So let's go to transform, compute, sample chi, the value of which will come out because of this variance. So what would that be? That would be 10 minus 1, 9 times the sample variance. Let me just put in directly this, which was the variance, divided by the number against which you are checking, which was the sigma naught square, whose value was given as 2.25. So sample chi value is 20.62, and you have to compare it with a critical value. So what is that critical value? That critical value is that the chi-square, that critical value for which the probability of chi-square being greater than that is 0.05. So let's compute variable again. Target variable is some critical value, and that I will get by doing let me see if you are able to see it. Yeah. By going to inverse distributions and inverse chi-square. So what you need to put in, you need to put in the probability, but since it computes the cumulative probabilities, so I need to put in 0.95 instead of 0.05. And over here, I have the numbers of degrees of freedom, which are 9. So when I compute that, I get 16.92. So that means since sample chi-square turned out to be bigger than this number, so I can reject it. So based on my computations, this number was equal to 20.62. And since it's greater than the critical value, which turned out to be 16.92, so H naught is rejected at alpha is equal to 0.05. But I can also compute, let's compute the p-value. So that would be the probability that chi-square 9 is greater than this sample value. So that we can, this is 20.62, so we can easily compute it by going to SPSS again. And this time, I do, let's say call it p-value. And this time I'm computing a probability, so it's not the inverse distribution, it's the cumulative distribution. Cumulative distribution of chi-square, which is given here. And my quantity is 20.62. Well, actually, this will give me, since it will give me the cumulative distribution, I have to find, starting from the tail, from the left tail up to this value of 20.62. But I need it starting from 20.62, going to the far end of the right tail. So I just do 1 minus. So the quantity is 20.62. Degrees of freedoms are 9. So the p-value is 0.01. P-value Now we can do another example. So this is problem 9.50 from book. So one way they're saying that uh, a teacher assigns a class to a teaching assistant, and they want to know that how much is the variation in the test scores taught by this particular teaching assistant. Are they doing better or are they doing worse? If all of them were taught by this teaching assistant, will their variance in the test score, because they want all of them to do good, will the variance be increased or decreased? So from historical records, they know that the variance used to be 300. And now this new teaching assistant has taught 30 students whose test scores were recorded, and their variance of these 30 students' test scores turned out to be 480. Now they want to know that what would be, that is, will all the students taught by this, so if I take, well, let me say this, if I take a large population of students taught by this TA, will the population variance be sigma naught square is equal to 300 or not? Now we can devise many kind of two different kind of alternate hypotheses depending on what we want to test. So suppose that the null hypothesis is that sigma is exactly equal to this, that the students taught by this TA will not be no different from what historically has been happening, that their their variance is 300. Let's test it against that the variance will actually change. It will not be 300. At alpha is equal to 0.5 significance level. So I'm going to divide the significance in these two regions and compute these numbers. Chi 29, what I had been calling 1 minus 0.025, and chi 29.025. So the upper critical value which I'm just denoting like this, and lower critical value. These are the numbers which I want to compute. So I do that by going to SPSS. Let me open a new file. And let me just put a random number here and start computing. So I want upper critical. I have to go to inverse distributions and inverse chi-square. Over here, for the upper, I want to have the upper tail to have an area 0.025. That means in this cumulative distribution, I have to put in 0.975, and the degrees of freedom are 29. So I get 45.72 for the upper critical value. And now I can compute the lower. And this time I have to put in 0.025 because the lower end, it just computes the cumulative probability. And I get 16.05 and 45.72. These are the chi-square values. I have to compare them with what I got in the sample. So sample chi-square value, again, is just n-1, 29, times whatever I got in the sample, s square. So what I had got in the sample was 480 divided by the assumed population mean value. So this gives me 46.4. So I barely defeated the upper critical value. So I can say, so let me first write over here the critical values. So upper was 45.72 and lower was 16.04. And I get that n-1 s square over sigma naught square is equal to 46.4, which is greater than the upper critical value. So H naught is rejected. The student's variance will change. Our evidence is showing that the variance in the student score is changing under this new TA. Now we can do another example. Um, so let's do this problem 9.52 from the book. So it is known that in some subject that from historical record that population variance of student score is 18.2, and the teacher brings in a new method of teaching, and she actually claims that this new method is gonna reduce this variance because they want to every student to do good, so they want to reduce the variance in the uh, test scores. And to prove that, she assumes that under her new method, the population variance is actually going to increase. It's going to be more than this, equal or more than this. And she will try to reject it to prove this alternate hypothesis that the variance in student score is actually going to decrease. So she teaches this course and gives a test to 30 students, 25 students. And for these students, the exam results showed a variance of 15.3. Now, this looks smaller than this assumed value, but we're gonna test that if it's small enough so that based on this we can reject H naught at let's say 0.05 significance. Well, this time let's not even do 0.05. We have some evidence over here that the variance is probably decreasing. So let's just compute the p-value for this evidence. So what she's gonna do, she's gonna assume a critical value for chi-square 25, which is going to be equal to, since she's doing less than, this is equal to her sample result. And just compute the probability. Probability that the chi-square 24 could be less than, well, this is not 50.3, has to put in this. So it's less than this value. And now this becomes, that would be the p-value, this area. So I get 24 times 15.3 divided by 18.2. Chi-square 24 less than this number, which is 24 times 15.3 divided by 18.2. So this gives me 20.17. And this probability I can probably just compute by going to stat track. So degrees of freedom 24. Critical value is 20.17. So I get a p-value of 0.31. This is a very large p-value. This implies that I cannot reject at alpha is equal to 0.05 or alpha is equal to 0.1 or even alpha is equal to 0.2. I can only reject it at 0.31, which is almost worthless. So that means H0 is not rejected at any considerable significance level. So she cannot prove, she doesn't have the evidence to show that her new methods are reducing the variance of students' test scores. So I'm going to stop here.